Hello everyone, my name is Keenan Burnett and I'm a PhD student from the University of Toronto. In this paper, we attempt to answer the following question. Do we need to compensate for motion distortion and Doppler effects in radar-based navigation? On the left-hand side of the slide, we have a picture of Boreas, our data-taking platform which includes a LiDAR, radar, and camera. This video was taken during a snowstorm in Toronto, conditions that most autonomous vehicles today would struggle to operate in. The main goal of this research is to develop a radar-based localization system that can approach the performance of LiDAR-based algorithms in ideal conditions while surpassing their performance in adverse conditions. Our chosen spinning radar presents several challenges, including motion distortion and Doppler effects. In this paper, we discuss the importance of these effects and present a method for removing them. This slide illustrates the primary advantage to using radar. On the top row, we can see what the data looks like during a sunny day. And on the bottom row, we have data collected during a snowstorm, where we can see that the LiDAR point cloud becomes littered with the detections associated with snowflakes. However, the radar data appears almost the same, except for the movement of large vehicles. For those who are unfamiliar with the Navtech radar, I will spend a little bit of time explaining how the sensor works. The Navtech sensor is a spinning mechanical radar which makes use of frequency-modulated continuous wave radar technology. The sensor spins at 4 Hz and provides 400 measurements per rotation, resulting in an angular resolution of 0.9 degrees. The sensor can be configured to have a range between 150 and 500 meters, with a corresponding range resolution between 4.4 centimeters and 17.5 centimeters. Each measurement consists of a power range spectrum corresponding to the intensity of the received signal at each range bin. These measurements together form a polar radar image, as seen on the top right. For many of our algorithms, we prefer to work with a bird's eye view representation, which can be created by warping the polar image. There have been many recent contributions towards radar-based navigation. However, I'm only going to describe what we consider to be the canonical radar odometry pipeline. This work was presented by Sen and Newman in 2018 and was one of the first to demonstrate large-scale outdoor ego motion estimation with a scanning radar. Their approach uses handcrafted feature extraction and descriptors. The main idea here is that they're using a median filter to remove the bias from the signal and subsequently estimate the noise statistics. They then use this noise model to scale each detection by the probability that it is not noise. They describe each feature using their radial statistics descriptor. The descriptor works by converting the detected feature locations in polar coordinates into a Cartesian grid. This grid is then divided into azimuth slices centered around the target feature, and statistics are calculated for each slice. These statistics are then arranged to form a histogram, which forms the final descriptor. In order to remove outliers, they use graph matching. A compatibility score is computed between each pair of matched features in order to create a symmetric compatibility matrix C. They then formulate finding the optimal data association as a graph matching problem, as shown in this equation, where each entry in the vector m is either 0 or 1 corresponding to a valid match. They relax this problem by replacing m with the vector u, where each entry is within the interval between 0 and 1. After solving for u star, they approximate the optimal solution using a greedy algorithm. The final SE2 transform is then estimated normally. So far, existing works have made significant progress in applying radar to odometry and place recognition. However, these works have so far ignored the impact of motion distortion and Doppler effects on radar-based navigation. The radar sensor rotates in order to provide 360-degree coverage around the vehicle. Figure A shows what this looks like when the vehicle is stationary. So what happens is that when the vehicle is moving, the range measurements become distorted in a spiral fashion, as shown in Figure B. Radar sensors of this type calculate range by measuring the difference in frequency between the received and transmitted signals. However, when the vehicle is moving, the relative velocity between the sensor and its surrounding environment causes the received frequency to be altered according to the Doppler effect. Figure C shows what this looks like. An increase in the received frequency causes the apparent range of targets to decrease. Our approach is to use a motion compensated estimator to calculate the linear and angular velocity of the sensor directly. We can then use this estimate to compensate for both distortion effects. Our pipeline follows closely from Sen and Newman's 2018 work. We first extract features using the same detector as theirs. However, We opted to use orb descriptors due to their ease of implementation and robustness to noise and minor rotations. The initial data association is obtained by performing brute force matching using Hamming distance on the orb descriptors. We also use a nearest neighbors distance ratio test to remove potential outliers. Finally, these matches are fed into our motion compensated estimator, and the inliers are shown on the right. Other works assume that the radar point cloud is collected at a single instance in time. Since the sensor is rotating quite slowly while the vehicle is moving, this assumption can result in erroneous predictions. The principal idea here is that we want to estimate the velocity of the sensor instead of a single rigid transformation. Our approach uses the real timestamp of each measurement and directly accounts for motion distortion. In the figure here in the middle, we have 3 pairs of matched features. Other works estimate a single transform to align all the radar pairs. Our approach uses a different transform for each pair of measurements, which depends on the difference in time between the matched features. This allows our method to account for the motion distortion. This work relies on the motion compensated RANSEC formulation that was initially shown by Sean Anderson in 2013 and applied to a 3D scanning radar. The key assumption that this algorithm makes is that the linear and angular velocity between frames is approximately constant. The transform Tm between each pair of features can be written in terms of the time difference between the pair of features, delta Tm, and the estimated body-centric velocity, pi. The cost function that we're trying to minimize is the weighted squared error, where the weights are determined by the inverse covariance of each pair. So, how do we get a body-centric velocity from this cost function? We first rewrite the velocity in terms of a nominal and perturbation component. We then make use of a small post-change approximation to optimize the cost function with respect to the optimal velocity perturbation. We can then use this velocity update in a Gauss-Newton optimization scheme until the estimate converges. If you want more details on this method, please have a look at my paper and Sean Anderson's as a reference. So the next thing we're going to look at is how does the Doppler effect impact our measurements and what we can do to compensate for it. On the top left-hand side, we have a diagram of a frequency modulation pattern of an FMCW radar. The main thing to note here is that the frequency of the transmitted signal is being modulated over time, with the blue waveform being the transmitted signal and the red waveform being the time-shifted received signal. FMCW radar calculate range by measuring the difference in frequency between the received and transmitted signals. So what happens is that when the target is moving towards the sensor, a Doppler frequency is induced according to the Doppler effect. This effect causes the received signal to be shifted up, so that's the entire red waveform. This then decreases the received and measured frequency change and thus decreases the apparent range to a target. The diagram on the top right is meant to illustrate the geometry of this problem. If we know the velocity of the sensor, we can calculate a simple radial correction factor, which is shown on the bottom right. This can be applied to each feature location in order to remove the Doppler distortion. Fortunately, since our algorithm is estimating the velocity of the sensor, we can use this estimate to remove the Doppler distortion in addition to the motion distortion. Our first experiment is to test the importance of these distortion effects on the odometry problem. For this experiment, we used the Oxford radar dataset, released by Dan Barnes et al. In 2020. On the left-hand side of this slide, we have a diagram of our odometry results. The results show that compensating for motion distortion can have a positive impact on odometry accuracy. The table on the right shows that compensating for motion distortion improves our results by about 10%, while the Doppler effect is negligible for this problem. For our second experiment, we perform metric localization against scans taken while driving in the opposite directions. To do this, we drove along a particular route and matched scans taken during the forward pass against scans taken during the return trip. For this experiment, we only kept frames where the vehicle was moving at least 10 meters per second. The histogram on the left illustrates the large improvements to metric localization accuracy that can be obtained when compensating for both distortion effects. The table on the right summarizes these results in a quantitative fashion, where again, we see that there are large reductions in error when compensating for motion distortion alone, and both effects together. In this video, we demonstrate the performance of our handcrafted radar odometry pipeline on data taken using our own platform. On the top, we have our camera data as a reference. On the bottom left, we have the inliers of our estimator, with red and green being the colors of subsequent scans. On the bottom right, we are plotting our estimator's path in blue against the ground truth shown in black. The main thing to note here is that we were able to estimate the eco motion with a relatively high degree of fidelity using only the onboard radar data. In conclusion, we have shown that motion distortion is an important factor for radar odometry, and we have shown that both distortion effects should be compensated when doing radar localization. For future work, we will be presenting a paper at RSS on the topic of radar odometry combining probabilistic estimation and unsupervised feature learning. We are also interested in moving away from the odometry problem towards full mapping and localization. In addition, we have been working on collecting a new dataset, which we hope to make publicly available in the next year. Our code for this project is publicly available and can be found on my personal Git repo. Thank you, and I'll be happy to answer any questions you might have.